Welcome, my name is Sven Schroeder, and I'm going to give you an overview over the activities that are going on in the advanced characterization theme within CMAC. I'm based at the University of Leeds, but also at Diamond Light Source, and I'm leading the group, the CMAC group in the research complex at Harvard. So what do we do in advanced characterization? Well, our mission is to develop new applications of advanced analytical techniques that help us to underpin the process research and the product research that is going on within CMAC, including the development of new processes. We focus on developing inline and in situ measurements, and the important thing for us is that these techniques can give you the deep understanding, the new insights that you need to move development from trial and error, from reactive development of techniques without the deep understanding necessary to have predictive capability into that area of managed development and innovation. There's a discovery aspect as well, in the sense of that the moment you start looking with advanced techniques, even at processes that you think you're familiar with, quite often you do find actually interesting new features and get new ideas. So I will give you an example later of where we've actually discovered a new habit of transient habit of lovastatin crystals that is very interesting to take forward into the future. And we're providing, through our in situ measurements and also through high throughput measurements, data for modeling and design. Yeah, so overall, if you look at this sort of management diagram here, process and development R&D management diagram here, where we're sort of looking at the tension between good understanding and not so good understanding of what you're looking at and available data, where we basically would like to be in that green quadrant at the bottom left, where you can actually manage the process because you know your system, you know what you know. We basically work on moving from the other three quadrants into that area to underpin the development and provide the knowledge transfer that enables the predictive design and control that is necessary. I'd just like to single out that the one particular thing that we found where we can be very useful is basically looking at what it's often called unknown unknowns. So basically the area of process properties and product properties where things are happening that are unforeseen, disruptive. We have no idea that they're going to happen. They need to be reactive in research. We can be very quick through the advanced techniques that we're using, moving from that area back into the green quadrant down there. So an example of what we're doing, I'll give you three main examples and then a summary at the end. So it's an example of what we're doing is we've developed pair distribution function mapping of molecular structure onto properties for liquids. So this is a big challenge in structural science, because liquids have very large degrees of disorder quite often, and you need to understand the sort of local structure and its relation to collective behavior of the whole liquid. So what we do is we look at pair distribution function analysis with the synchrotron X-rays, so we get very high energy X-rays, and we can then rapidly map through whole phase diagrams with structure analysis, and then get structural models by fitting against those scattering data that we're getting with X-rays. So what I'm showing you here in the middle is we have looked at, for example, acetone water mixtures. I'll show you the raw data and the fits that we get from the structure modeling against those data. Then on the right-hand side, you can see that there's a diagram that summarizes the self-interactions of acetone with acetone molecules and water molecules, which shows that you've got very strong deviations from ideal behavior. So the red lines don't coincide with the straight ideal lines in this diagram there. which shows us that the acetone-water interactions, so the non-self interactions, are actually the dominant feature in the acetone-water mixture. And that then, if you go into detail, enables you to actually understand things like, for example, the deviations from ideal behavior in distillation, azeotrope formation in distillation. Yeah, so I'm showing you a vapor pressure diagram for the system here at the bottom right. But a lot more. So we can also understand the variability of solubility, dipole moments, and so on in these systems as a function of composition. The nice thing is it's quick, so you can do basically your whole binary phase diagram, for example, in a day now, and we can do in situ and inline time-resolved crystallization measurements as well. Another technique we're using is surface analysis, where we are bringing an instrument that's been funded by the Henry Royce Institute at Leeds into the fold at CMAC. So we're contributing to understanding of how the surfaces of our crystallization products are influencing their subsequent processing, and how the surfaces are related, for example, to habit formation. So an example that I'm showing you here is for mefenamic acid, where the surface composition varies as a function of crystallization and washing conditions. And basically what you're seeing here is that the top spectra, the top 3 spectra here on the right-hand side, are for mefenamic acid form 1 in the solid form, crystallized in one particular way, and the spectra below that you can see they're significantly different. These are spectra of material obtained from aqueous solution, and you can see that the surface composition, surface properties are quite significantly different. Third technique is X-ray radiography and tomography, where we're going beyond what's traditionally called radiography, which is actually absorption radiography, where you basically get contrast in X-ray radiography just due to the mass density variation and the absorption variation of the materials that you're looking at. So we're dealing with the fact that in organic systems often you get poor contrast, because basically the composition, the elemental composition, and the mass density variations between different organic materials are quite low, and as a result you get limited absorption contrast, which doesn't mean to say that it's not useful at all. I mean, there's a lot of very useful X-ray, micro-X-ray tomography work going on, for example, with the instrument up at the University of Strathclyde. This is here taken from the work of Frederick Dorr, who looks at formulations, at crystals, at particles, and gets their internal structure and their external structure, and relates that to formulation behavior, processing behavior, and product performance. However, we can go one further now using Synchrotronics and use the fact that we can use coherent X-rays, and with coherent X-rays you do get an additional contrast mode, and which arises because as coherent X-rays penetrate through 2 different phases, at the interface between the 2 phases, they interfere, and due to refractive index changes between 2 different phases, so for example here for a solution and a crystal, you then get these interference effects that give you additional contrast. So that allows us to do things like this. So we're looking at an anti-solvent continuous anti-solvent crystallizer together with the Ansevchik's group from Strathclyde, where we're interested in basically understanding how we can bring the anti-solvent crystallizer, this continuous flow and anti-solvent crystallizer, into a controlled predictive state. The overall aim being that you want to have flexible, more scalable, more cost-effective ways of making your crystals. And the challenge here is that we need to understand the fluid dynamics. We For example, we don't know what the local supersaturation in these systems is. We need to understand liquid-liquid phase boundary influences, and also the influence of mixer geometry in wall materials, and we need to look at the local mass transport and phase dynamics. Yeah, so we need a microscopic real-time imaging process, which has phase and chemical sensitivity, because we're dealing with a spatio-temporally complex process. This is a sketch of the concentric flow antisolvent microreactor. The important thing is that we've got two concentric tubes, and in the mixing region, one of the inner tube ends, and you do get mixing due to the contact between the two liquids at that point. And basically what we're doing is, within that region that I've just circled in red here, we look with the X-rays, with X-ray imaging, at what is going on in the crystallizer. This is what the experiment looks like at the synchrotron. And here I'll show you some of the results. So this is a snapshot. This is a real-time technique. So this is a snapshot of it on a time scale of 30 milliseconds, where you can see all kinds of parallel crystallization processes going on here. You see homogeneous nucleation, you see oiling out, heterogeneous nucleation, transient crystals with plate habit being formed. These are the crystals I was mentioning earlier. So we do actually find a new habit of lovastatin, which seems to be templated by the reactor walls, and seems to be a transient phase from which the nucleation of the more common needle-like crystals of lovastatin is taking place. So what this shows us here is that the antisolvent crystallization process is actually much more complex than you would perhaps expect based on sort of standard models for antisolvent crystallization. There's a lot more going on in terms of supersaturation and non-equilibrium thermodynamics. So the great learning that we take away from this is that you've got to be careful in designing your process, because you might get things like oiling out, coalescence of these oil droplets, then heterogeneous nucleation in parallel with thin film formation, and then nucleation from the film, and of course the traditional homogeneous nucleation that you would expect, all leading to some sort of crystal growth. So disentangling that, the X-ray imaging is very, very useful for basically telling us about all of these features. It's almost like a Swiss Army tool that allows us to look into this and get our bearings. Many other applications. We're working with Chris Price on his team on filtration and washing, and with John Robertson, Alistair Florence, and Gavin Halbert on and their teams on twin screw extrusion. To finish, what we have in advanced crystallization within the advanced characterization within CMAC is a very vibrant, very active research network. I'm giving you a list of all the people involved, but that's not a complete list. On the left, and you can see we've got Bath, Strathclyde, Leeds, Imperial, all interacting with each other, and Diamond and the research complex at Harwell sites. I've mentioned the Henry Royce Institute interaction already. What I didn't mention is that we actually also work with NPL on some of these techniques. So it's a worldwide unique combination of fundamental and applied crystallization research with large facilities. So thank you for your attention, and thank you very much.